So we are now going to prove, we'll begin the proof, the actual proof, the proof proper of the convergence of Fourier series. So let me just state exactly what we're going to be proving. Sorry, I've rearranged my office and some furniture's in the way. Okay, so we're going to say, let's say we have a function f. F is continuous. On the interval minus pi to pi. Its derivative is continuous. On minus pi to pi. Okay, and really what we want is we want it to also be periodic. So the way that we're going to state it, the thing that we really need to be true is we need to have f of minus pi minus 0, so the limit from the left is equal to f of pi plus 0. We need to have something like this, and we need to have similar for the f prime. F minus like this is equal to f prime of pi plus 0. Sorry, actually I have this backwards. It needs to be like this. Okay. So in other words, if I look at minus pi, the limit from this side, and if I look at the at pi, the limit from that side, those should be equal to each other. So this is going to be the limit from the right at minus pi. This will be the limit from the left at pi. Okay, and so what we're saying is that in this case, the Fourier series for f, which is given by this formula here, ak cosine kx plus bk sine kx, this converges pointwise to f of x. In other words, if you just think about the partial sums here, I mean, what this is saying is that if you look at the partial sum here, for any value of x you plug into, as n goes to infinity, this sum is going to go to f of x. Okay, and again, we're assuming we have this additional assumption that f is continuous on this interval, f prime is continuous, and this thing here about this thing here about the limits. Another way to think about this, another way to think about this, I mean, this is kind of strange. Another way to think about this is that we want f to be like periodic, or we want its periodic extension to be continuous, and f prime to be continuous as well. So we want its periodic extension to be continuous, and we want f prime, the periodic extension of f prime, to be continuous as well. Would be another way to achieve these two things here, because if a function is continuous and differentiable, its derivative is also going to be, if a function is continuous and differentiable and periodic, its derivative is also going to be periodic. And that's really what we need. I'll explain where we need that. It's going to be at one point we do a computation, we're going to need that we can have something like this. Okay, we're going to need to know what happens if we take the derivative basically around pi and minus pi. Okay, so how are we going to do this? Well, remember that our formulas for AK are as follows. AK is equal to 1 over pi times the integral from minus pi to pi f of y cosine ky dy, and then bk is similar except with a sine instead of a cosine. So minus pi to pi f of y sine ky dy. Okay, so now what we're going to do is we're going to just compute what this is. Okay, with the n there, you'll see why we can't do it if we have an infinity there. we're basically just going to write out what the AKs and BKs are and rearrange some stuff. Okay, so when we do this, so, and by the way, I'm going to call this here S sub n of x, meaning the nth partial sum. So we're like fixing an f here. And then this really depends on f, but I don't want to explicitly write the dependence. So we're fixing an f, and this is the nth partial sum. And so Sn of x is equal to 1/2 a0 plus the sum k equals 1 to n. Okay, so what is ak? ak is going to be 1 over pi, so I'm going to pull the 1 over pi out of here. 1 over pi, the integral from minus pi to pi, f of y, cosine ky, and then cosine kx. I'm just going to put that both in the integral. The integral will be with respect to y. And then I'm going to have something similar for sine. So it's going to be plus sine of ky, sine of kx, dy. All right, now f is a good function. We're assuming f is continuous. Each of these functions is a good function. It's continuous. It's a finite sum, so there's absolutely no problem. There's no ambiguity, nothing at all wrong mathematically, nothing that needs to be justified at all about interchanging the integral and the summation. The only thing that I'm going to need to do is look at my notes, because there's going to be some tedious things here that I need to make sure that I get right. All right, so now what's going to happen here? So I'm going to do something with this in just a minute. I want to get this all into one integral, and I'll do that in just a second. So this is 1/2 a0. I'm going to interchange this integral, and this is going to be plus 1 over pi times the integral from minus pi to pi. Okay, again, I can factor out an f from the sum, so this will be f of y times the sum k equals 1 to n cosine ky cosine kx plus sine ky sine kx dy. And now let's recall what a0 is. Well, a0 is just, so I'm going to have my 1/2 from there. a0 is 1 over pi times the integral from minus pi to pi f of y dy. Okay, so I basically want to combine this into one integral. So I've got an f of y there and f of y there. I have a 1/2 here, so I'm going to factor out a 1/2. So I'm going to multiply this by a 2 and have the 1/2 there. Okay, and then I'm actually just going to move this 2 into there. Okay, so just some algebraic manipulations there. This is a pi up here, kind of looks like there's a prime going on. Okay, so now what's happening, what I can do now is I can factor out a 1 over 2 pi. And now I'm going to have an integral from minus pi to pi f of y times 1, the 1's coming from here, and then plus 2 times the sum k equals 1 to n cosine ky cosine kx plus sine ky sine kx dy. Okay, now through a sequence of algebraic steps, tedious algebraic steps involving trigonometric identities, Euler's identity, things like that, we're actually going to show that we can write this as an explicit function, like without the sum. Okay, so it almost seems miraculous what we're going to be able to do here. And so we're going to, like I said, we're going to be able to write this as a function with an explicit formula. The name of the function is called the Dirichlet kernel. So this function here is going to be, or not is, but this is called, well, actually, let me do one more step before I can tell you what it's called. So the next step that I'm going to do is the sum of angle, the sum of sine and cosine, whatever you want to call it, identity for that. And so this will be equal to 1 over 2 pi times the integral minus pi to pi f of y, and we're going to have 1 plus 2 times the sum k equals 1 to n, and then this is equal to cosine k of x minus y. And now this sum, the thing that we have in the brackets, not just the sum, but the 1, 2, this thing that we have in the brackets here, this is called the nth Dirichlet kernel, and this is equal to, it's defined as this function right here. Okay, so notice what we're saying then. What we're saying then is that the nth partial Fourier, the nth partial Fourier sum is equal to the convolution of f with this Dirichlet kernel here. Now we've mentioned briefly things about approximations to the identity, and it would be very, very nice if this is an approximation. If this was an approximation to the identity, things would be very, very nice. What does approximation to the identity mean? Meaning basically this is a positive function whose integral is equal to 1, and it goes to 0 as x minus y. As the argument goes away from 0, this argument goes to, or the function itself goes to 0. Okay, so they're like peaky functions. Now this satisfies some of those properties. Its integral is equal to 1, but it's not positive, and actually the amplitudes don't go to 0 as we go away from 0. And we've already seen this. We've already seen something like this before when we did the Fourier inversion formula. And we just kind of said at that point, well, this is kind of going to work out like we want it to work out. We just kind of said it's not an approximation to the identity, but we can treat it like an approximation to the identity, and we never really explained why, or I never really explained why. Well, in the next video, I'm going to explain why this actually satisfies, it's not an approximation to the identity, but actually that as n goes to infinity, this will go to f of x. So again, if we want to write this out a little more explicitly, this is 1 over 2 pi minus pi to pi f of y kn of x minus y dy. Okay, and my claim that I will pick up proving in the next video is that this goes to f of x. Okay, so in other words, I want to say that this function kn of x minus y, this converges to the Dirac delta distribution in the sense of distributions, meaning that it's, for any function that I put here, this integral is going to go to f of x. Okay, I'm not saying that as n goes to infinity, this pointwise goes to the Dirac delta function. That's not what I'm saying, and we'll see that doesn't really make sense. Pointwise, as n goes to infinity, this limit doesn't exist. But in the sense of distributions, this does go to the Dirac delta distribution. That's essentially what we're going, not essentially, that's exactly what we're going to prove in the next video, the next 1 or 2 videos. I don't know how long it'll take. But in the next video, I'm going to show kind of this minor miracle. This is actually going to converge to a function with a very nice form that's going to allow us to do all sorts of wonderful analysis here.